Welcome to Understanding Signal Isolators, Converters, and Interfaces. Let's start by revisiting the key takeaways from Part 4. In Part 4, we focused on how isolators function in real applications. We looked at area isolation for safely sharing signals between systems, splitting signals to allow multiple systems to operate independently, isolators that eliminate bucking power supply conflicts, and transmitter excitation that powers two-wire devices directly from the isolator. These functions show how isolators do much more than protect signals. They help solve practical design and maintenance challenges. In Part 5, we'll continue building on the functional roles of isolators by looking at additional ways they solve real-world process loop challenges. We'll show how isolators can boost an overburdened loop by adding drive capability, selectively pass or block HART signals for better diagnostics and control, reduce cost and panel space using multi-channel designs, and apply custom linearization to correct nonlinear process measurements. These functions expand the role of isolators beyond protection, making them powerful tools for optimization and integration. Over time, signal loops that once worked fine can become overburdened as additional devices are added. A typical loop-powered transmitter, supplied with 24 volts, can only drive a limited load. When the total loop resistance exceeds the drive capability, signal accuracy can suffer, or the loop may stop working altogether. A signal isolator solves this by boosting the signal's drive capacity. Powered by the receiving system, the isolator reduces the load seen by the transmitter while creating a new output loop with its own drive capability. This restores stable operation without replacing the transmitter or rewiring the loop. Depending on the application, a signal isolator can either pass or block the HART signal. When access to transmitter diagnostics and configuration is needed, a HART-enabled isolator allows the digital HART signal to pass through to the output loop. This lets technicians connect a HART communicator at any termination point on the loop. To do this, the isolator must be specifically designed to pass the HART frequencies without distortion. In other cases, blocking the HART signal is preferred, especially when older receivers are sensitive to noise or when configuration access needs to be restricted. In these situations, a standard isolator with strong common mode rejection prevents the HART signal from reaching the output loop. Multi-channel signal isolators combine multiple analog signal channels into a single instrument, helping reduce both panel space and overall cost per point. Instead of installing individual isolators for each loop, a multi-channel unit handles several signals in one compact package. These instruments can be used in nearly all the same applications as traditional isolators and converters, including signal splitting. For example, a 4-channel isolator can take one input signal and deliver 4 fully isolated outputs to different receiving devices, making multi-channel designs a practical and cost-effective choice for high-density installations. Microprocessor-based isolators and converters offer capabilities that go beyond traditional analog devices, and one of the most powerful is custom linearization. Custom linearization allows you to define a specific input-to-output relationship by plotting a custom curve inside the instrument. This is especially useful for non-linear processes, like converting tank level into actual volume, performing square root extraction, or characterizing pH or valve behavior. Instead of relying on an overloaded PLC, the isolator handles the linearization directly. By entering strapping data or curve points into the PC configuration software, the isolator outputs a scaled 4 to 20 milliamp signal that accurately represents the real process value. In this video, we've covered several ways isolators and converters add flexibility to modern control systems. We looked at how signals can be boosted to overcome long distances and heavy loads, how multi-channel instruments reduce cost and panel space, and how signal splitting allows one measurement to serve multiple receivers. We also explored custom linearization, where microprocessor-based devices handle complex signal relationships directly, reducing the burden on the control system while improving overall accuracy. Together, these capabilities show how the right signal interface can simplify design, improve performance, and help ensure reliable data reaches every part of the system.